Hi, I'm Preetham. I'm the DC1 for the project Night LiDAR. I'm working right here at Thales. In this project, we are developing an photonic electronic integrated FMCW LiDAR that will reduce the footprint as well as increase the effective efficiency. You can see behind me in the board, there's a schematic of FMCW LiDAR. FMCW stands for frequency modulated continuous wave. That is nothing but we change the frequency of the source over time. In our scenario, we change the frequency over time linearly. That is called linear chirp, and we transmit this chirp to the free space. Now coming back here, we create the linear chirp. Now we split into two parts. This segment is responsible to maintain the linearity of the chirp, and this one is for the detection. Here also, if some portion of light is taken out, that is called local oscillator, and other portion of light goes to the free space via beam steering system. This system may be a dispersive grating, MEMS mirror, or OPA, optical phase array. Then it goes to the free space, hit the target, and we get the received signal, and we combine the received signal with the local oscillator, and we get the beat signal. And this beat signal frequency is nothing but the difference between the transmitted and the received chip. And if we take the signal processing FFT, then we get the power spectral density and we get the frequency of our beat signal, and the information of the distance is embedded in the frequency. Now here we are using dual chirp, that is triangular chirp. Because of this kind of chirp, we get the information of the radial velocity as well as distance simultaneously. That is the benefit of FMCW LiDAR. We can measure the distance as well as the radial velocity simultaneously. You can see the formulas here also. Now, after having the information of the radial velocity and the distance of each point, we can create a point cloud of our surrounding or a 3D image of our environment. Now let's jump into the test bench and see how it looks like. This is the setup I built with off-the-shelf component to benchmark different key factors like nonlinearity of our chirp, the phase noise of our source, dispersing beam steering system, impact on our detection. Now, here is the laser source that we modulate, and then we collimate through it, and the collimated beam passes through our dispersive grating as a beam steering system. And this is the reference interferometer, which measures the nonlinearity and to maintain the linearity of the chirp. And this reference interferometer is for the detection. Now let's zoom in and see. Now if you see closely, there is a triangular waveform that is used to modulate our laser to create a triangular chirp. And this is the beat signal of our reference interferometer. And if we take the Hilbert transform of this beat signal, we get the information of our chirp. And if we compare it with a ideal chirp, we get the non-linearity of our chirp. And this is the detected signal. And if we take the Fourier transform of it, we get the power spectral density and the frequency peak, and our information of distance and velocity of the object is embedded in those frequency peaks. Now let's look at closely how a dispersive beam steering system works. We have the collimated beam, then it passes through the dispersive grating, and if you tune the wavelength of the source, then our dispersive grating will deflect the beam in different direction. That's how we get the beam steer. And after putting a camera next to the dispersive grating, we captured the image of the beam steer. Here you can see frame by frame the beam is moving. That's how a beam steering system by a dispersive grating works. As DC1, I oversee the LiDAR system from beam steering to digital signal processing, ensuring seamless integration every step of the way. So at the end of this project, see you with the complete integrated FMCW LiDAR setup. Until then, peace out.